Oh, hi, I didn't see you there. Welcome to IPC. Today, we're going to walk down memory lane and talk about forces. As you may remember, there are 4 fundamental forces of physics. There's gravity, it's little, and as we go down, we get bigger and bigger. We get stronger. We have gravity, we have weak nuclear force, or just weak force, the electromagnetic force, and strong force. If you remember, force is simply defined as a push or a pull, And the SI unit for force is newtons. A newton is the force it takes to move 1 little kilogram, 1 meter in 1 second. That's the definition of a newton. So it's just, you're going to push 1 kilogram, 1 meter in 1 second, and that's approximately 1 newton. Next, we learned about a little force called gravity. Gravity, let's say it together. Remember we did it, the law of gravity? It is an attractive force between 2 objects that depends on their mass and the distance between them. I know y'all can do better than that. I need y'all stand up at home, and I want you to do it with me at home, just so you can remember what it feels like to be in IPC class. It's an attractive force between 2 objects that depends on the mass and the distance between them. Hopefully that's ringing a bell. So one of the forces of physics is gravity. Now it is a field force. That means it doesn't have to be in contact for it to feel it. And an example of gravity is the Earth and the Moon. They're not in contact, obviously. There's a huge distance between them, but they're also very massive. So there's an attractive force between the Earth and the Moon. Gravity is an attractive force, and it can be felt over great distances. Next, we talked about the electromagnetic force. Now, if you can see, there's 2 parts to the word electromagnetic. We have electro, and we have magnetic. We have, so if you think about the electric forces, they're the charges that you maybe see in lightning, or if you rub your feet across the floor, you build up electrons on yourself, and you reach over and you touch your brother's ear and it shocks his ear, or maybe you touch a door handle. That's an electric charge, right? We also have magnetic forces. And again, these are attractive and repelling. These also attract and repel. And you're familiar with magnets. Obviously, the north and the south attract, the north and the north repel, and the south repel. So electric charges repel and attract. If you remember that if you have a positive and a negative charge, electric charge, they will attract. If you have 2 negatives, they will repel, and if you have 2 positives, they will repel. These are also field forces. They don't have to be touching in order to feel that repel or attraction. Now, humans finally figured out that the electric force and the magnetic force work together, and the electromagnetic force has changed all of our lives. It's why we can have class at your house on your computer with electricity. We learned a couple of 100 years ago that when you have a flow of electrons or a flow of electric charges, it generates a magnetic field. And when you have a changing magnetic field, it generates electricity, or the flow of electrons. It induces a current. And that's why we have electricity. If you remember in class, I demonstrated this by showing you that if I create a flow of electrons in this series, I can make this. I can make the magnetic field even stronger by wrapping it around a piece of metal. And when it wasn't previously a magnet, right? If I put a current, a flow of electrons through it, suddenly it becomes a magnet. This was called an electromagnet, if you remember that from class. If I disconnect the current, it falls off. Another example of the electromagnetic force is when we have a changing magnetic field, north and a south, north, south. If it's rotating, and if it does it a lot, it's going to induce a current or make those electrons start flowing, and you're going to see the light bulb turn on because I have induced a current. I've induced the electric flow there. So that's just a little reminder how humans have luckily made our lives a lot easier with the electromagnetic force. Question, is the electromagnetic force greater than gravity? Well, I'm going to do something that you guys just love to do so much. you will remember from last semester, you took these airplanes and you somehow threw them up and made them stick. I'm not very good at it, obviously, but I'm gonna put something up there. I'm gonna take this magnet and I'm going to see if I can get it to attract to the metal up here. I'm not tall enough, but I'll give it a try. Ah! Stand by, I have another magnet just in case that didn't work. Let's try another one. Are you ready? Ah, so what does this tell us? What does that magnet tell us? That magnet is telling us that the electromagnetic force that's causing it to stick up to the ceiling is greater than the force of gravity pulling down on it. So to answer the question, is the electromagnetic force greater than the force of gravity? Yes. All right, now the last thing I want to talk about. Whew, got a little out of breath, climbing up a ladder, 3 steps. The last thing I want to talk about is the electromagnetic force and how it is used to hold the nucleus together. In the nucleus, or in an atom, we have 3 particles that make it up. We have the proton, which is positive, the neutron, which has no charge, has mass, but no charge. We have the electrons out here in a cloud around the nucleus, the middle part's the nucleus. What's keeping these electrons close to the nucleus? The nucleus has an overall positive charge. The electrons are negative, so that negative and that positive, we know, are attracted to each other. The positivity of the nucleus and the negative electrons hold that atom together. It also is used like in ionic bonds. When we have a positive cation or we have an anion, and those stick together to form a chemical bond. But what I want to really bring to your attention, and it's my last point, is let's just take a peek at this nucleus right here. If we get rid of the electrons and just focus on this nucleus, we have all these positive charges in here. What do we know about positive and positive charges? Positive and positive charges repel each other, right? How are they staying packed in there together? They should be trying to get away from each other, right? What keeps that nucleus together, what keeps those charges that really want to get away from each other together, is the strong force, the strong nuclear force. And it's the strongest of all the fundamental forces of physics. And it's like a ribbon or a rubber band or a belt that's keeping those protons that really want to get away from each other together. And that is called the strong force. And we will pick up on, we'll talk more about the strong force in the next section. I do want to draw your attention to one thing. We've talked about the forces of physics and of nature, and there is one force that's even greater than all of these. And that's Christ. He is stronger than any power or any force in the universe. He proved that on Easter Sunday, which we just celebrated, when he overcome death even. So thankfully we serve a really powerful God. That's all I got.